Hi, I'm Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Sebastian Luber of Infineon. We're going to talk today about quantum computing technology. Sebastian, we've been looking at quantum computing now for years. It's been coming down the road as this will be the next big thing. Where are we today with quantum? What are we capable of? What's still missing?
A comparison which I like very much is when you compare the current state of quantum computing to the computing we know, to the standard digital computing. And there people very often say we are roughly in the 40s, perhaps 50s of the last century. So you could say we already have the first proof of principles. And these results are amazing. So we have demonstrated, or colleagues have demonstrated, that quantum computers are capable of doing things which you are not able to do with our current computers. So that's really very impressive. But beyond this proof of concept, beyond these first examples, the current quantum computers are not able to do something useful, especially not relevant for the industry or for society. So we need some further development steps to overcome this, to really come to the point where they can be used in real and relevant applications. And there is still much work for us to do, so still a long way to go.
Two of the biggest problems that have been sitting out there have been, one, how long do the qubits last? And the second thing is, can you do enough with those qubits to do something actually useful and have enough accuracy?
Yeah, that's correct. We are already able to do something, but these are rather academic problems to solve, or academic problems to demonstrate exactly this potential of quantum computers. And the basic elements, the qubits, they are not performant enough yet to really use them for longer, for more complex calculations. The most important development work still to be done to make these qubits more reliable, to preserve these special quantum properties of the qubits for longer time. So these coherence times have to be improved significantly, at least for part of the qubits. And then we need much more of them, of course, because currently you're still very much limited. We have a few dozens of qubits. We need hundreds, thousands, or perhaps even more if we talk about error correction. So to putting many of these qubits together to be fault tolerant, because this is also the second problem, so that you have a lot of errors within your calculations. So after a few cycles of calculation, you can't distinguish the result anymore from pure noise. So one way out of that is this quantum error correction, so that you bundle a lot of physical qubits to logical qubits, which are then safe, which are fault tolerant. And by that, you hopefully then soon will be able to address these relevant applications.
So really what we're doing here is taking what we've learned in other parts of computing and now saying we can apply some of these concepts into the quantum world, right?
At least part of it. It helps a lot. This experience from the classical computing helps a lot as well with quantum computing. But with quantum computers as well, you have very specific quantum properties where the classical computing experience does not help you. So you have to combine this understanding of the quantum world, of these very specific features, with all the expertise, especially engineering expertise and programming expertise from the standard computing world. But perhaps also one important topic, talking about production or manufacturing. So having this huge development going to smaller and smaller nodes in standard computing and semiconductor chips, of course, this helps a lot, and even probably enabled now this fantastic development in quantum computers. So the ability to control such small structures, to manufacture them reliable, and combine a lot of structures. This is also something which is needed to manufacture quantum computers. But you also need this very specific understanding of these quantum properties, and there are some specifics to be dealt with.
So let's take a closer look.
Sure.
What are we looking at here?
Here I want to demonstrate that quantum computing is part of quantum technologies. So in principle, going into the quantum world, so making use of these very specific quantum effects like superposition or entanglement or even uncertainty allows you to address topics which you can't do with a classical world, with the classical approaches. And you can use them to build quantum sensors to do very accurate sensing, for example. You can also use this principle to do a very secure communication. So by nature, guarded communication to prevent any eavesdropping. You can also use these principles to build advanced simulators, especially to simulate the quantum world. And of course, we can also, as you know, we can build quantum computers with this. And that's, of course, one of the most fascinating topics to address completely new fields which you are not able to access with standard classical computers.
This is not the kind of device you're going to take home, though, right? I mean, a lot of this stuff has to be done cryogenically at very, very cold temperatures.
That's correct. There are a lot of different ways to build a quantum computer. I mean, in principle, you need a physical system with two different energy levels or properties. And there are many, many different ways to build them. But as I already stated, these systems are very susceptible to the environment. So whenever you have some changes in the environment, you introduce noise, you disturb the system. So one way to protect them is to cool them down. So especially to get rid of these thermal excitations, this thermal noise. Many systems, so for example, the superconducting materials itself, they need usually, at least the classical superconductors, very, very cool temperatures. And then you even cool them down to temperatures like 10 or 15 millikelvin, so really close to absolute zero, to prevent any thermal noise to influence your system. But it's also possible to use other kinds of technologies, other kinds of platforms, like, for example, diamond or ions, which in principle would allow you to operate them at room temperature. So it's not excluded that in future we will also have room temperature quantum computers, but for the moment it just helps to cool them down. So all of the platforms, even the ones which are capable to be used at room temperature, are cooled down to extremely cold temperatures. But usually these are closed loop systems, so you don't need to hook it up to a helium line or whatever. So if your space in your basement is large enough, you could even put them at your home.
You get some other effects as you start cooling things down to those kinds of temperatures too, right? So you get some superconductivity out of DRAM and things like that, which really speed up the whole system as opposed to just what you're trying to do with the chips.
That's correct. There are very, very interesting aspects, especially when you combine technologies. So, for example, you can build a quantum computer based on semiconductors in a semiconductor system. People now look into using superconductors as gate metal because it has a lot of advantages, because it doesn't dissipate heat, so you don't introduce heat again into your system. And talking about speed, so if you build a quantum computer from superconductors, you also need to control the behavior. I mean, you need a lot of standard silicon, a lot of circuits, a lot of your electronics in order to operate the quantum computer. And there's also one way to build part of that in superconducting logic, which is one part of this your circuit logic, which has been developed in order to get rid of the speed limitations of standard silicon. And there it helps again. So superconducting logic makes logic extremely fast, and it can also be used in order to control a quantum computer. So kind of the fields kind of come together. You have a mixture, a melting pot of different approaches, and it's still open which one is the best one to scale up to more powerful quantum computers.
There's been a lot of talk about how this is going to be used to crack some of the existing security protocols that are out there and technologies. Where else do you see quantum computing moving to? What sort of applications?
I think one of the important aspects you already mentioned, so quantum computers having these unique properties allow us to address fields which are not accessible by standard computers. And one of them, which also pushed the development of quantum computers, is a field of security or cryptography, which exactly relies on these types of problems, which are hardly solvable with classical computers. And of course, one implication of a future quantum computing age, or you could say, is that you have to prepare exactly for that. So you have to make your cryptography, your methods safe, even in a quantum computing world. And there are ways to do that. So you either can use quantum effects themselves or use standard methods in this post-quantum cryptography. Let's jump to the application to the right-hand side of this slide, talking about the different fields where you could use quantum computers. It's in a lot of industries. So wherever you have currently in your company or in your application challenges where you need a lot of computing power, and especially your standard computers hardly give you the right solution, it's exactly there where quantum computers could make a difference. And to give some examples, for sure, it's the chemical industry. So I've been surprised. I mean, I'm a physicist. I come from the semiconductor industry, but in chemical industry, it's extremely difficult to accurately simulate chemical reactions. There are ways to do that with standard computers, with classical computers, but it's extremely difficult to get accurate and fast results. And there are ways to do this with quantum computers, which promise to give you better results there. Another example, so even in our own company, you have a lot of optimization problems. So for example, in logistics or in supply chain, we have millions of orders. We have to match them to our capacity. And to make here the best fit, we currently use a lot of approximations. And if you could do this in real time and could even save a percentage point in capacity of your semiconductor fab, this is a huge leverage. And there are much more possibilities to apply them. Of course, being a semiconductor supplier, we also want to be part of this emerging market. So we are currently working on several platforms where we can use our existing technology, our existing know-how, which we have in-house, and leverage this for the use in the quantum world. And these are 3 platforms, actually. So it's semiconductors, so spins and silicon, it's superconductors, and it's ions.
So let's dig into those 3 a little bit, because I think those are really interesting challenges as we start trying to develop the new qubits. What has to change here, or what is changing?
Let's perhaps start with superconductors. It is one of the most advanced platforms. There are a lot of players working on superconductors. The first success has been mainly by using lab methods in order to fabricate and to build such a first prototype of a quantum computer. But what we need is much more performance, much more powerful quantum computers to really use them in relevant applications. And now what we need is to apply all the knowledge, especially from semiconductor industry, to scale this up to higher numbers of qubits, to more performant qubits, to much more reliable production, so that every qubit is performing as expected. And that's exactly what is needed now in the superconductors. In addition, of course, to make the qubits much more performant.
When you talk about performance of these qubits, what actually are you talking about? Is it speed or is it time that they last?
For superconductors, it's more the time which they last, so this coherence time. Superconductors itself, so the operating speed, the time which you need in order to operate or to do a gate operation is very short, so they are very fast. But the drawback here is that they really lose these quantum properties which you need very fast. So just after a few cycles of operation, the qubits kind of lose their information and you're done. So we have to work to improve that, either by further improving the qubits, there are a lot of ideas to do that, or by combining them and you're living with these kind of properties, getting some results.
What are ion qubits?
So ion qubits is using atoms or ions as the basic element to build a quantum computer, so to use them as qubits. And the motivation here is, if you think about superconductors, so for superconductors, you can think of them as artificial atoms. You design explicitly the properties of these qubits, but you have to live with the imperfections in manufacturing them because you artificially create them. So you can think of, why not letting nature help you in building qubits because nature had a lot of time to design things. And that's exactly what you do when you use atoms or ions as the basic element. It gives you the great advantage that, especially for ion qubits, these coherence times are extremely long. They are extremely stable. So if you have very, very long time in order to operate on them. Of course, you have to live with other drawbacks. For example, they are slower than superconductors. All in all, you could say that each platform has some advantages and some disadvantages to live with.
The new kid on the block here is the spin qubits, right?
Yes, exactly. This is also a very, very fascinating platform, but performance-wise, you could say that currently, at least with the number of qubits, they're a bit behind the other two platforms. But here, the promise is that you can repeat what we have seen for the standard semiconductor industry, that you have an extreme fast scaling up to higher numbers, because you can leverage on the experience from semiconductor design, from semiconductor manufacturing. And that's what we are hoping there, especially to make use of this experience. And the basic principle there is to use single electrons. So you use your semiconductor to catch single electrons, and these single electrons then have, again, these properties which you need in order to build a quantum computer.
So which of these technologies do you actually see becoming commercially available, and will the other ones still be developed alongside of those for specific purposes, or is it going to be one or many?
I think at least for the midterm, we will see many platforms in parallel. There's really a race going on. I mean, you have many players betting on one or the other platform. There are different development steps on one platform. Then it's kind of saturating a bit. Then you have other developments. And what I would expect is, having the current hardware limitations of the current quantum computers, that the first applications or the first quantum computers useful for any kind of applications will be very specifically designed for this application. And having these different properties of these different platforms of superconductors, ion semiconductors, and all the others, I suppose that one of them might be better suited for one application, for example, for this chemical simulation. Others might be better suitable for another application. So on the midterm, I think that we will have many platforms in parallel. On the far future, when you really solve all the technical, all the engineering challenges, it could be that a single platform then evolves, which is, let's call it the winner, but it's still a long time, I think, until we reach that state.
If you go back probably 10 years ago, before AI and machine learning came into computing, we tended to think in terms of very finite numbers. So when we did computing, there was a right answer and a wrong answer. When we started getting into AI and machine learning, we started getting into probabilities. The same applies in terms of quantum computing, right? We're still working in probabilities, but those probabilities is now what we're measuring as the accuracy. How high can we get on the accuracy scale in terms of this percentage correct?
Absolutely. So whenever you enter the quantum world, you leave these finite numbers and you have to deal with probabilities. And now it's a big challenge to design or to create algorithms which then still give you the right answer or the wanted answer and deals with these probabilities. So we have a few examples where we have great results where algorithms do exactly that, so that reducing the uncertainty to a level we can live with that, or even giving with 100% probability then the right answer. But in general, yes, it's another approach. It's a different way of thinking, of designing things, and you have to live with that. But I think for a lot of applications, especially ones we already discussed, it's possible also to live with this kind of uncertainties. So with a small margin of error, it might still give you a lot of advantage in your application. For example, in chemical reactions, it might not be the most accurate result, but if it's accurate and especially fast, it can still speed up your development, for example, for a drug or for a fertilizer or a catalyst or whatever. to a significant amount.
And also, just to put this in perspective, we've really been working with quantum mechanics for years with the development of chips. This now pushes our world a bit further into the quantum realm, right?
Exactly. The difference is that now we really can manipulate these single or specific properties of single particles of particles of the quantum world accurately. Before, of course, even a transistor cannot be understood or designed without understanding and without the laws of quantum mechanics. Completely right. But now we really manipulate the properties of single electrons or single atoms, and that's the difference. Yeah. But interestingly, to me, these both worlds tend to come together. I mean, the lithography nodes of the standard semiconductor industry become so small that quantum effects become more and more important. So you also more or less reach this point where you are already at the quantum computing world. So there's not much space left, and perhaps we will see a combination of both then later in a semiconductor chip having a quantum processing unit as well as a standard computing processing unit. So could be then, we see everything on the same chip.
Sebastian Luber, thanks for a fascinating glimpse into a really interesting technology.
You're welcome. It has been a pleasure. Thanks a lot for having me.